Hello and welcome to video 40, and for my students I hope you're enjoying your snow day. I also hope that you can enjoy your physics from home on the nice comfy couch or wherever it is you like to enjoy your physics. I'd like to talk about a situation known as simple harmonic motion. You guys have seen this in class. We actually did a lab with this. Simple harmonic motion occurs anytime you have what's known as a linear force, meaning the force is proportional to the distance or some other factor, and it's got to be a restoring force. Notice as this mass goes up towards the top, the spring squishes and tries to press it back down. How hard it presses depends on how squished that is. So the equilibrium point is somewhere around here. So the only place at which it doesn't experience a net force is when the spring force is exactly equal to the weight force somewhere around here. But this force, in principle, will cause this object to keep going in this uniform motion, or simple harmonic motion, I should say, forever, as long as there's no energy loss. So let's analyze this motion and try to come up with the equations of motion, and we're going to do that in terms of energy. If you go on to take, for example, AP Physics C, you'll do this in terms of calculus, but for today I just want to do it in terms of energy. So let's draw a line here, and I'm going to represent the mass at 3 different locations. This is going to be the line at which the spring is not stretched at all. This is going to be where x equals 0, x being the stretch of the spring. Now, just as an aside, if you remember, the spring force is always equal to negative the spring constant times the x, the negative being it's a restoring force, and you can see it's a linear force, the kind that we need for simple harmonic motion. And if it goes above this point, it's going to compress the spring, and the spring's going to push down. And that distance, you skip to a skinnier marker. This distance here I'm going to call A, so it's some distance A above that midpoint. At this point, it's worth noting that this mass has a velocity of 0. This is when it's squished all the way at the top. The second place we want to consider is the mass when it is right at this midpoint here of the motion. At this point, the spring is at its rest length. The stretch or distance x is 0. This is also where it's going to be moving the fastest, because once it goes past this point, the spring is going to start pulling it up and slowing it down. And the third place we want to consider is the lowest point that the mass reaches. And that is going to be a distance negative a. So the spring is going to be stretched negative x. So the magnitude of the force, or negative a rather, the magnitude of the force that it feels here will be equal in magnitude to the force here, but in the opposite direction. So here the force is pushing it down, here it's pushing it up, and obviously in all 3 cases it has a mass of m. Now let's look at this in terms of the energy. So if I call these positions, let's call them A, let's call it T that for top. Let's call it M for middle, and let's call it B for bottom. At all 3 points, it should have the same total energy. That total energy is always going to be comprised of a kinetic energy, an energy of motion, and a potential energy from the spring. Now recall the potential energy equation for spring is 1/2 kx squared. K being the spring constant, x being the distance that it's stretched. So let's go ahead and write this equation for the very top part. So the total energy at the top is going to be equal to the kinetic energy at the top, which is 0 because it's not moving, plus 1/2 k times the amplitude squared, because a is the distance x. So that should be the total energy of the whole system. No matter where you are in this system, that should be the same. We could do the energy in the bottom, and it would really look the same. If we were to do total energy at the bottom, it would have no kinetic energy. And it would have a kinetic energy, okay, of negative a squared. That's going to give you the same thing. Where it gets interesting is when you look at it in the middle here. So if we were to look at the energy at the middle position, it does have kinetic energy. And that kinetic energy is going to be 1/2 m times the velocity squared, keeping in mind this is the velocity in the middle, plus 0, because at this point there is no potential energy in the spring. It is neither squished nor stretched. Now, from before, using conservation of energy, we know that the energy in the middle, let's switch colors here because we can, the energy in the middle should be the same as the energy at the top if energy is conserved. So the energy in the middle, the 1/2 m velocity at the middle squared, should equal the total energy, which was the same as the potential at the top, which was 1/2 k x squared. Use a skinnier marker here in red. It can cross out the 1/2. Sorry, this x here is a, because at the top it was a. And when I solve for the velocity at the middle, I bring over the m, and I'm going to get k over m a squared equals v m squared. So let's take the square root of that. Well, let me write it like this. And the way I prefer to write this is the velocity middle. I like to take the square root of the first part, k over m times a. And this will tell us the velocity at exactly the midpoint, which is going to be the fastest it ever moves. And that velocity is going to depend on the spring constant, the mass, and the amplitude at which you initially disturb it. There's all things that kind of make sense. But by now you might be wondering, well, what if I wanted to know what the velocity was at any point along here in this motion? If I wanted to know the velocity at any point, I would take the total energy is still going to have to be this 1/2 kx squared. So let me actually write it out formally. The total energy is going to have to be equal to the kinetic energy plus the potential energy at any point, not just the top, not just the middle, not just the bottom. But that total energy is going to be 1/2 k a squared. The velocity is going to be 1/2 m v squared. And the potential energy is going to be 1/2 k x squared. Now, this works for any point. We're going to cross off the halves here, or as I always jokingly like to say, the have-nots. I'm going to bring this over here, so you're going to get, let's stick with the black, the thick black. I'm going to get k a squared minus k x squared equals m v squared. So I can factor out the k, divide over by the m. I'm going to get k over m times a squared minus x squared is going to equal v squared. Or, taking the square root of both sides, I'm going to get that the velocity at any point in this motion is going to be equal to the square root of k over m times the square root of a squared minus x squared. And they'll give me the velocity at any point in this up and down motion, in this swinging. It's worth noting that if I look at the special case where x equals 0, if I look right here, I should get the same velocity we got here. And if you plug it in, you do. If you look at the velocity for a position of 0 meters, that's going to be the same as the square root of k over m times the square root of a squared minus 0. And lo and behold, you get square root of k over m times a, the same velocity as we got before. So we now have an equation that will tell us the velocity at any point in this motion. I just want to take a second and show this to you in sort of a picture form. This is a classic concept that translates throughout physics when you're analyzing anything that undergoes simple harmonic motion, and that's to look at it as sort of an energy graph. So if I was to make a plot where I put the position on the bottom here, so this is actually going to be the x, and this is going to be the energy. I'll draw this sideways so you can kind of envision you've got a spring attached to a mass, and it's oscillating back and forth between these 2 points. So at these 2 points, the velocity is 0. And if we go ahead and we make this the position that is 0 meters, or whatever unit you choose, excuse me, this is going to be a position of negative A, and this is going to be a position of positive A. Keeping in mind that the potential energy of a spring is 1/2 kx squared, you would expect to get some sort of squared relationship or sort of parabola. And I just draw a line like this so you can see. You expect to get a potential energy function that is going to look like this. This is the potential energy. Now, the amount of energy in the system is constant. So if we make some line, some amount of energy that's in the system, which in the case of the spring here is going to be dictated by where you started it, how far you stretched it, you will find that the potential energy plus the kinetic energy is always going to have to equal a total. So graphically, the distance between these two is going to be the kinetic energy, and over here, this is going to be the maximum amount of potential energy you can get, and over here, this is going to be the maximum amount of kinetic energy you can get. And as we've mentioned before in class, sometimes because potential energy is always really measured relative to something else, sometimes it's useful to think of this as 0 potential energy, and potential energy decreasing, getting more negative. But I'm not really going to get into that too much. But this is also known as a potential energy well, and you need to exceed some amount of energy to quote-unquote escape that well. It's also worth noting that this is a stable equilibrium. You keep oscillating about this point, and this is dictated by the restoring force. So if you go this way, the force is going to restore you this way, much like gravity, which is also a linear force, is going to restore you towards the bottom of a hill. So this is just a picture I want you to keep in mind. So we've now talked about the velocity. I know I'm a little long-winded, but let's talk about it in terms of position. And here's where, rather than using calculus, we're going to look at this as if it was something in circular motion. And you may say, what do you mean? Our buddies at Wikipedia have put this together, which does a nice job. If you look at the motion of a mass undergoing uniform circular motion, it is actually the same as if you looked at just the y component of an object undergoing uniform circular motion, or in fancy terms, there's a phase space. So the velocity is related to the position. So when the position is way up here, it has no velocity, but then shortly has a negative velocity as it goes on the way down. And then right about here is where you have the greatest negative velocity when it's heading down, like right now. And then it slows down to 0, and then it starts to speed upwards in the upward direction. That's where this comes from. But this uniform circular motion is something we know. We have a lot of practice with uniform circular motion. We can use that to get at the position equation for this mass. If we assume that the y component of this circle is always going to be equal to the position of this mass. One way you could do this, it's kind of cool, is if you shine a flashlight on this, you'll see it follows this. Let's look back here. Here's a picture that I borrowed from YouTube. You can see the link there. And what I was trying to say in words before, I'll try to show you graphically now. And that is that if you look here, this has some amplitude, which is equal to the radius of this circle. And for some generic position, so if this is A, let me switch over to the thinner marker. If this distance is A, and this is theta, the y component of this is going to be equal to A sine of theta, the opposite side of the triangle. So y equals A sine of theta. Here's where it gets interesting. If you recall from uniform circular motion, if you're moving at a constant velocity, it is always angular velocity, that is. It is always going to be true that your angular position is equal to your angular velocity times the time. So I can actually rewrite this as y equals A times the sine of omega, or w, times t. So that is one way that we can write the angular position, or the y position. We also know that in terms of plain old frequency, omega, or w, is always equal to 2 pi times f. So y is going to be equal to A sine 2 pi f. That's another way you can write this. Or, because we know plain old frequency is equal to 1 over period, we can actually write this as A times the sine of 2 pi t over t, the period. So this will give you an expression that gives you the vertical position. Okay, when we do this, I want to point out an assumption we're making, and that is the assumption that when the time is 0, it's starting off right here at the 0 degree position or 0 radian position. But it doesn't have to be that way. You could technically start anywhere on this circle. I just want to point out, if we were to start here, what that would mean is when time is 0, when the t is 0, wt, or whatever function you take of wt, would have to be equal to 1, so that the amplitude would be A. The easiest way to make that happen would be y equals A times the cosine of omega t. It's also worth pointing out that this is equal to A times the sine of omega t, but you shift it by some amount, some 90 degrees, some pi over 2. This difference here is often called the phase shift, or sometimes we use phi. You can actually get this to start at any time you want by making this anything you want. Although, really, what we tend to make it is either 0, pi over 2, pi, 3/2 pi, etc. For my students, we're not really going to do a lot with that phase shift. I just want to let you know that that's out there. So I'll just leave it at that for now. Let's talk about the velocity of this as it goes around in terms of a circle. If we're assuming this is uniform circular motion, we're going to pretend that it is an object going in uniform circular motion, meaning constant speed, and the speed at which it goes is the same as the maximum speed of this block when it goes around. Now, from the other page, you can remember the velocity maximum, which is at the midpoint, is equal to k over m square root a, or more generally, square root of k over m times a squared minus x squared. Take the square root of that. But this is going to be the velocity right here, here, really everywhere. And if it's going in a circular motion, and you want to figure out what the time is, or what the period is, you're going to assume that it goes around a circle. So we're going to assume that the tangential velocity is equal to the distance around a circle, better known as a circumference, divided by the time to go around a circle once, better known as the period. Now, the tangential velocity we're going to assume is k over m square root of a, the same as the maximum velocity of this block, the velocity at the midpoint. And that's going to be equal to the circumference, which is going to be 2 pi times the radius, which is going to be the diameter. In this case, it's going to be a diameter of a, the amplitude, divided by the period, which is the thing that we want to know. Now, notice the a's actually cancel out, and you're left with a period t that is 2 pi times m over k. Now we have to take the square root of pardon me, we don't have to take the square root of anything. It's already square root. This is an expression that gives us the period. Notice the more mass on the spring, the larger the period's going to be, and the stronger the spring, if you will, the bigger the k, the shorter the period's going to be, and that certainly makes sense. So we now have an expression for the period. I also want to write an expression for the w, the angular velocity, keeping in mind, let me pop back to the thinner marker here, keeping in mind that omega is 2 pi times the frequency, which is the same as 2 pi over the period, which means it's going to be 2 pi over the period we just found is 2 pi. Now when I divide or flip that, that's the same as times k over m. Take the square root, the 2 pi's cancel, and you get the angular velocity is going to be equal to the square root of k over m. The last thing I want to derive for you is another useful expression for the velocity, and right over here on the left. The velocity from before was the square root of k over m times the square root of a squared minus x squared for any, or square root of that, for any position as the spring's going up and down. But what if you want that in terms of angular stuff? The k over m doesn't change. The a doesn't change. But x, remember, if you look at this, the x position is going to be, now by the x here is really the same as the y component of this, is going to be the a sine of theta. So this is going to be the same as a sine of theta squared, which is going to be a squared sine squared theta. Keep that under the square root sign. I'm going to pull out the a's. So that's going to be a squared times 1 minus sine squared theta. So we would be saying, wait a minute, I know that. That's like a really important trig identity. That's the same as a squared times cosine squared theta. And take the square root of that, and you're going to get k over m equals a cosine theta. Oops. Times b equals. And the last thing, if you recall from over here, square root of k over m, we can write that as w. So we now have an expression, v equals omega a cosine theta, which means if we know the angular position and the angular velocity and the amplitude, you can get the velocity at any location using those things. The last equation that we're going to use in this course, although I'm not really sure how one would derive it without taking the derivative of this, the acceleration linearly at any point is going to be equal to omega squared times a sine omega t. So if I was to just write sort of a summary of the equations that are on the sheet, let me be clear. I'm not expecting you guys to derive these on the fly, at least not this year, maybe next year. Equations you need to know. Spring, negative kx is the force. And these are all in the reference table. Y equals A, technically plus or minus, sine of omega t, which is the same as plus or minus A times the sine of 2 pi times the frequency times time, which is equal to plus or minus A times the sine of 2 pi t over big T, or the period. The velocity of the spring, or the mass on the end of the spring, or anything undergoing simple harmonic motion, is going to be the square root of k over m times the square root of a squared minus x squared. The period is going to be equal to 2 pi square root of m over k. That's an important one. In terms of angular velocity, yes, it's 2 pi f, but it's also equal to the square root of k over m. Notice without the 2 pi and flipped. The period of a pendulum is useful to know. Perhaps some other time we'll derive that, but for today, it's just given. The velocity in terms of angular stuff is going to be omega a cosine omega t. The acceleration is equal to omega squared a sine omega t. And just for good measure, because we're in the waves unit, let's finish the equations. V equals f lambda, and t equals 1 over f. So these are the equations. They're all given to you, but you need to know what they are. I just wanted to give you a sense of where they come from. I understand many of you are probably asleep by now, but someday you may actually come back to this and say, oh, that's where they came from. At least that's my... Let me just give you a for example. I actually have in school, and I'll show you when you guys get here, a ring stand with a spring on it, and I hung 1,700 grams, better known as 1.7 kilograms, from it, and I measured the time for it to go up and down 10 times. What that does is that allows me to actually calculate the spring constant pretty accurately. When I did this, it took me 7.38 seconds for 10 cycles, a cycle being all the way up and down. Now this is very much the kind of thing I am expecting to be able to do. So the equation that we came up with in this really long video, sort of like a class, is 2 pi times the square root of m over k. Notice the bigger the mass, the longer the period. But let's say we want to use this for k, because this is actually a more precise way of measuring the k value for a spring than just kind of eyeballing the stretch distance. So to get rid of this, this is going to be t over 2 pi equals square root of m over k, square both sides. You're going to get t squared over 4 pi squared equals m over k, where k equals m times 4 pi squared over t squared. The t that we plug in here is going to be 0.738 seconds. The mass is going to be 1.7 kilograms. So when you plug that into your calculator, hopefully you get the same thing I got, which is 123.2 newtons per meter. That's the spring constant I got for this mass. Then, it's too bad you can't see it. It's a thing of beauty. I changed the mass so that it was 1,000 kilograms. And let's now calculate the theoretical period of this pendulum, or this oscillating mass. So we're going to take, again, 2 pi m over k, and it's going to give us 2 pi. The mass I used now is 1 kilogram. The k we're going to use from before is 123.2 newtons per meter. Take the square root. And when I do that, I get a time that is 0.566 seconds. Now, this is the kind of thing that makes your heart melt, at least mine. When I did this, I got 5.72 seconds for 10 oscillations. That is really close. I don't think we even need to bother doing the percent difference. This is the kind of thing you very much have to be able to do. You're not going to have to derive all these equations, but you are going to have to calculate the period based on the mass and the spring constant. What you're looking at now is actually data from a lab we did earlier in the year, although I didn't make as big a deal of it at the time. At the bottom we had a motion sensor, and hanging above that we had a mass attached to a spring, and it was oscillating back and forth. So it's exactly the situation we're studying now. It's simple harmonic motion. All I did with that data is I shifted it so that the position the mass was in when time was 0 was right at the length where the spring is not pulling or pushing. So it's rest length. Now, the equation that we just derived a few minutes ago for the position, the vertical position of the mass is y equals a sine omega t. Now, I want to point out with these numbers, what it's essentially, and I'm rounding a little bit here, you're getting 0.0078 or 7.8 centimeters times the sine. The omega we're getting is 17.16 radians per second times the time, plus if there is any shift, it'll show up here. That shift here is small enough that I'm going to basically ignore it, although it's not quite 0 because this doesn't start off at 0. And that gives us the position function. Now, worth noting, something we want to check is we can get the period from the W. Remember, W equals 2 pi over period, so the period should be 2 pi over W, which gives you 2 pi divided by 17.16. And when I put that into my calculator, the time that I get is 0.366 seconds for the period. Now when you look, the time from here to that same time looks like it is about 0.33 or 0.366 seconds. So that seems to line up very well. So it's really cool, at least I think so, that this graph shows us that this number here is the A, which in physical terms is the maximum amplitude of the displacement from the rest position. So if it's going back and forth between here and here, this is going to be 7.8 centimeters, and this is going to be negative 7.8 centimeters. It's oscillating back and forth. This is the omega, which we just calculated, and from that we can get a period, 0.366 seconds, and that seems to match. Now, we can also look at a graph of the velocity. Notice the velocity starts off at a high number as fast as it goes. And the reason is, when this mass is at a rest position, or at least the spring's at its rest position, that is its point of maximum velocity. The equation, theoretically, that we should get for the velocity equals omega times the amplitude times the cosine of omega times t. This is the theoretical equation that we came up with. Now, I want to point out that a cosine function is really just a sine function shifted by 90 degrees, or pi over 2. So this equation should be the same as WA times the cosine of WT plus pi over 2. The reason I'm writing that, sine. The reason I'm writing that is when this fit function was made, they use a sine function because really a cosine is just a shifted sine. I want you to look at these numbers, particularly this number right here. Does that look familiar to anybody? So if I start writing in the numbers, the W, 17.22, makes sense. That's similar to what we got before. sorry. The number we're getting in front of here, which should be the product of W and A, is 0.1256. We'll come back to that, times the sine of 17.22, which is close to the 17.16 we got before, plus 1.57. I have not changed anything. This number, if it doesn't stand out already, is pi over 2, which is pretty cool. This shows you that this really is a cosine curve. It's just shifted pi over 2. I don't think we need to calculate the period again. We can see that's almost the same number. This number we're expecting to be pretty close to W times A. So let's say we solve for amplitude. We're saying that AW equals 0.1256, or A is going to equal 0.1256 divided by the 17.22, and that's going to give us an A that is 0.0073 meters. So we get something very similar to the 7.8 meters we got before. I think that's cool. Now let's look at the acceleration versus time graph. So when you look at this graph, you can see it looks like a sine curve that has been shifted, or is negative of what a sine curve normally would look like. And that is exactly what you would see when you look at the theoretical equation, which was sort of just dumped in your lap, is negative W squared A sine omega t. In terms of the numbers we get here, this number, which should be equal to omega squared times A, is 2.023. We'll get to that in a second. Sine, the omega we get is 17.21, consistent with what we got before. This phase shift, 3.14, that's essentially pi, which doesn't really change it at all. Maybe it's lowercase a here, so to avoid any confusion. I don't think we need to check this. That's going to give us a period that's pretty similar. Let's see what we get for A. So we're saying that A omega squared should equal 2.023, or A should equal 2.023 divided by 17.21 squared, and when I do that, I get 0.0068, which is reasonably close to the 0.78 and the 0.73 that we got before. The last thing I want to show you that is perhaps the most fascinating, especially if you're somebody who takes calculus. Now the magnitudes are different because when you look at the different functions for acceleration, for velocity, and for position, what you're multiplying a sine curve by is a different value. But in terms of where they line up on the time axis, they're just shifted. In fact, velocity is shifted 90 degrees, which we saw, the 1.57, from position, and acceleration is shifted 90 degrees from the velocity, or 180 degrees from the position. So this graph is a negative sine curve. Now, I know this really isn't about calculus, but those of you who are taking calculus should be jumping out of your seats at this point. What, my friends, is the derivative of sine? The derivative of sine is cosine. What is the derivative of cosine? It's negative sine. And the acceleration is negative the sine of this. So each of these shifts it by 90 degrees, and each is the derivative of the other. I perhaps got a little out of hand here in terms of the length of this video. You don't need to understand everything that's in it in terms of deriving it, but you do need to be able to use those basic relationships that we wrote on this page. So everything that's on here is on your reference table. You're expected to be able to use everything, not necessarily to derive everything. I hope this is helpful. Perhaps if you go into AP Physics C or some other physics course, you might look back at this and find this useful. If you're still with me, I commend you, and I will see you in class. I hope you enjoyed your snow day.